Hi, I'm Tristan. This is Magic Maillard Maple, and today we're thinking about the science behind bread.
FoodSHOTS.
So we're still on COVID-19 lockdown, and home baking has become something of a national pastime here. Unfortunately, this means that people are struggling to get hold of small bags of flour, and people are finding it very tough to get hold of baker's yeast. So as an alternative to leaven their bread, some people are turning to sourdough cultures. So as well as learning about the science behind bread, we're going to also try and make some sourdough cultures of our own.
Specifically, we are going to compare two of the most popular sourdough recipes from the BBC and BBC Good Food websites. The first relies on the traditional method of mixing flour and water, leaving in a warm place so that it can be colonised by wild yeast and bacteria, and then feeding with more flour and water at intervals. Because this method is reliant on microbes present in the flour, environment, and also on whomever is making the starter, we would expect some variability between starters made in different kitchens. Our second method uses natural yogurt as a source of live bacteria, in this case a mixture of lactobacilli and bifidobacteria. Whilst our recipe calls for warm skimmed milk, we must be careful not to add milk that is above 45 degrees C to our yogurt, lest we kill off the bacteria. I'm also going to try to make my own beer bread starter. This follows the traditional starter recipe, but I've added the sediment from a bottle of my home brew as a source of live yeast. Whether the result will count as sourdough loaf remains to be seen. However, this is certainly an interesting way to kickstart a leavening culture. Growing the starters takes 5 days, and during this time we would expect the pH to decrease slightly as the lactic acid bacteria metabolize and multiply, and for bubbles of carbon dioxide to form. The yoghurt starter was the slowest to develop, whilst our beer starter began bubbling after the first day. All the starters develop their own distinct tangy, sour and sometimes boozy aromas that should add real character to the bread. Now that we have some viable starters, it's time to make the bread itself. This process can be broken down into 4 key stages. Stage 1 is the mixing of dry ingredients with water. A few interesting things are happening here. Firstly, starch granules will absorb some water and start to swell. This increases the viscosity of the dough. Second, this water will wet or hydrate the proteins in the flour so that they can uncoil and get to work. This includes amylases that will break down some of the starch into simple sugars. I covered how some of these work in episode 1, and also gluten, which gives bread dough its ability to capture air. Stage 2 is where we knead the dough. Traditionally this is done by hand, but today we will use a food mixer with a dough hook attachment. By folding the dough over and over again, we will incorporate air pockets that can be enlarged during proving. Most importantly, however, we will also provide the energy needed to form a gluten network, which allows the dough to trap air and expand without splitting apart. Gluten is sometimes referred to as the muscle of the flour. It provides dough with extensibility, elasticity, and expandability. Gluten network development will influence the final volume of our dough, the firmness of the bread, and how coarse our final crumb will be. Gluten is actually a group of proteins that can be divided into gliadins and glutenins. The end of each glutenin protein is especially rich in cysteine amino acid residues, which contain sulfur. As we knead the dough, we add energy to the system, and we keep bringing the terminal ends of different glutenin chains closer together. This energy, the extra air we've incorporated, plus any bread improvers we might add, all contribute to the oxidation of these cysteine residues, which results in the formation of disulfide bonds. Therefore, as kneading progresses, we increase the number of glutenin strands that are joined end to end, like springs, through the system. We will also form some hydrogen bonds between these chains. Taken alone, the glutenins would form a very stiff and inelastic dough. Luckily, we also have the gliadins. These chains are less able to form disulfide bonds and will instead sit between long strands of glutenins. Hence, the gliadins act as ball bearings, enabling sheets of glutenins to move past each other and back again, giving true elasticity to the dough. Slight modifications to our bread recipe can cause big changes in the end product. Small amounts of salt will improve the flavour, but it will also decrease electrostatic repulsion between gluten proteins. This will increase the level of non-covalent bonding between these chains and thus improve the overall strength of the gluten network. If we add fat, we will prevent the hydration of some of the gluten proteins and so will weaken the gluten network. This practice of shortening is the basis of several crumbly baked goods, from shortbread biscuits to flaky puff pastry. Now that the bread has passed our window pane test, we can move to the next stage. In stage 3, we allow our dough to prove. This is a process where we simply place our dough in a warm place and allow our microbial leavening agents to create gas and expand the existing air pockets in the dough. In episode 1, we covered the way that yeasts work, taking the glucose and maltose liberated by amylases and fermenting them to ethanol and carbon dioxide. When making a traditional bread, we would be using Saccharomyces cerevisiae, just as for brewing, albeit a different strain. However, in sourdough, we can find a range of other wild yeasts. For example, in a study of 14 sourdough sampled in France, Urien et al. Found the genus Kazakhstania dominated the yeast profile, finding the Humulus, Balderi, Solgenus and Unispora species in these dough. Interestingly, some of these wild yeasts, such as Kazakhstania humulus, cannot directly use maltose for fermentation, and this is where some species of bacteria can come in really useful. Of course, sourdough also contains a wide range of friendly bacteria, which can outnumber yeasts somewhere between 100 to 1,000-fold. The majority of these bacteria are lactic acid producers, that is, bacteria that convert glucose to lactic acid in order to generate energy. Depending on the species involved, this will be done via either the homo or heterolactic fermentation pathway, shown here. Lactobacillus sanfranciscensis is probably the most common lactic acid bacteria found in sourdough. This organism can convert simple sugars from flour to a mixture of lactic acid and carbon dioxide, giving a sour flavour whilst helping the dough to rise. However, this bacteria also has another neat trick that allows it to help out the other microorganisms in the dough. Specifically, it can use an enzyme called maltose phosphorylase to directly use maltose as a food source. However, for every molecule of maltose it uses, it also liberates a molecule of glucose. This glucose can then be used by yeasts that are otherwise unable to use maltose as an energy source, making the dough rise even faster. Despite all of this, sourdough takes a lot longer to prove than regular yeast-leavened bread. For our loaves, we will knot back after 3 hours of proving, shape and place into bowls covered with flour-lined tea towels, then we will leave to prove for another 3 hours before our final stage. After 6 hours of proving, we're finally ready to bake our bread. As the water and ethanol in the dough is vaporised, we will get a second rapid rise in dough volume called oven spring. Soon, the heat will cause the gluten network to set, and this forms the scaffolding of the bread. This scaffold is filled with a body of partially gelatinized starch granules, together giving us a soft but firm crumb. As the surface of the bread is much drier than the centre, and it is rich in sugar and proteins, baking will give us a crispy crust, as well as a golden brown colouring and cooked flavour through the Maillard reaction. After a 35-minute bake, all 3 recipes have risen in the oven and have a beautiful brown colouring. The yoghurt and traditional starter are similar in shape and volume, though using a rough volumetric calculation, we can see that the traditional bread has risen about 10% more than the yoghurt starter. My breads have a fine crumb, but to be honest, they're a little dense for my taste. I think a few more hours proving in a warmer room will help my results next time. By comparison, the beer bread is very well risen and has approximately 40% greater volume than either the yoghurt or traditional starter sour loaves. It also has a more coarse and open crumb that we would typically associate with a yeast-leavened farmhouse loaf. All 3 loaves have a tangy, sour flavour, quite unlike a typical bought slice loaf. It will be interesting to see whether these flavours will change over the next few baking days as the starters are refed and mature further. We could also use our established starter in a wide range of bakery projects, from pancakes to pizza. Well, there we are. I hope you enjoyed learning some of the science behind bread. We're off to enjoy a slice slathered in butter and some fresh homemade jam. See you all next time.